Okay, just talk about a velocity addition example that also allows us to transition into two-dimensional motion. Let's think about a swimmer in a river. And let's just say that that swimmer can swim at a velocity of v swimmer relative to the river. Swimmer SR, VSR. Velocity of the swimmer relative to the river. So that's how fast the swimmer swims relative to the water. The swimmer is attached to the water's frame of reference, and so the swimmer can only swim at that velocity relative to the water. So then the question is how fast is the swimmer swimming relative to the ground, right? So this is the wall. Oh, crumbs. Okay, I think I got it this time. So if the swimmer is swimming at v swimmer, I got it this time, SW, swimmer relative to water, right? So how fast is the swimmer swimming relative to the ground? I'll just call that FVSG. Swimmer's velocity relative to the ground or the shore. VSW, swimmer's velocity relative to the water. Okay, so let's just say, and maybe you've already thought of this, let's just say the water is not moving. So therefore, the swimmer is swimming relative to the ground at VSW, right? So in that case, if the water isn't moving, therefore, the velocity of the swimmer relative to the ground, or relative to the shore, or the banks, whatever you want to call them, is equal to the velocity of the swimmer relative to the water. And so therefore, let's just even ask a very explicit question. Let's say that the swimmer is trying to swim 100 meters as fast as they can, and the swimmer wants to go delta x along the shore of 100 meters. And let's say that they're swimming at what's a reasonable speed. So luckily you haven't had to bear with me in class in person, because if you have, I would have regaled you with more stories about my running and also my swimming. I was, for a very short time, for a couple of years, I was a triathlete about 10 years ago. And so becoming a triathlete, I had to turn from being a marathon runner to being a swimmer, runner, and biker. And I just sort of thought, hey, I'm a good marathon runner, so maybe I can be a good triathlete. Turns out that my swimming didn't help too much. I was an extremely slow swimmer. While I was able to swim long distances, I actually swam in a Ironman triathlon, which was 2.4 miles swimming. My speed was on the order of 1 mile per hour. It was a little faster than that, but it was about a mile per hour. For those of you who are swimmers, you know that's pretty slow. But a mile per hour is about half a meter per second. So let's say we have a swimmer who can swim at 1 meter per second. That seems reasonable. How long does it take the swimmer to go the 100 meters? So therefore, the amount of time that it takes, right, since the swimmer is swimming at a constant velocity, the delta x equals velocity times delta t. In this case, the velocity, and again, this is an equation for constant velocity, but in this case, the velocity is just 1 meter per second, so therefore, the amount of time it takes for the swimmer to swim 100 meters is indeed 100 seconds. Okay, now let's take a slightly more realistic situation, and let's assume that the water is flowing. And let's say that the swimmer is swimming with the current. And let's go ahead and give the water a speed. Let's say that the water is, and the velocity of the water is going to be, right, if it's flowing relative to the ground, then it's going to be the velocity of the water relative to the ground. And the velocity of the water relative to the ground might be in any direction, but it's likely upstream or downstream. And let's just call it whatever direction that is. We'll call it, it doesn't matter, upstream. And let's say that the water is flowing at what's a reasonable speed for water flowing. It can vary a lot. But for this, let's just call it 2 meters per second. So now The question I have is how fast, what is the velocity swimmer relative to the ground, the velocity of the swimmer relative to the ground, and how long does it take the swimmer to go 100 meters? Well, if the velocity of the swimmer relative to the ground, you should be able to look at this and figure it out. What is the velocity of the swimmer relative to the ground? The velocity of the swimmer relative to the ground is equal to the velocity of the swimmer relative to the water, and the water is pushing the swimmer at an additional velocity of the velocity of the water relative to the ground upstream. So that is the velocity of the swimmer relative to the ground. And this is in general. This is going to be generally true. If we have the velocity of, let me find a good color. If we have the velocity of object 1 relative to object 2, and the velocity of object 2 relative to object 3, then the velocity of object 1 relative to object 3 is going to be equal to this sum, just like this. So the velocity of 1 to 3 is equal to the velocity of 1 to 2 plus the velocity of 2 to 3. Now you got to be careful, right? That does not mean, right, velocity of 1 to 3 equals the velocity of 1 to 2 plus the velocity of 3 to 2, right, ground to water. This is not correct, right? The first one, whoops, let me correct that. So this one is correct. This one is not correct, because in this case, in this case, the velocity of ground relative to the water is opposite the velocity of the water relative to the ground. So there's a minus sign there. So it's always the velocity of the first object to the third object is equal to the velocity of the first to the second plus the velocity of the second to the third. So if I were to give you the velocity of the ground relative to the water, which would be silly, but you would have to take the negative of that, right? The velocity of the ground relative to the water is equal to the negative of the velocity of the water relative to the ground. It might make more sense to talk about two cars, right? The velocity of car 1 relative to car 2 is equal to the negative of the velocity of car 2 relative to car 1. So if I want to find the velocity of car 1 relative to car 3, the velocity of car 1 relative to car 3 is equal to the velocity of car 1 relative to car 2 plus the velocity of car 2 relative to car 3. Whatever that means, you can draw yourself pictures and figure it out. But this, let me not do that in blue. This is actually, even though it's specific to this situation, it's a general equation for any three objects, moving relative to each other. Relative velocity formula. This is called the relative velocity formula. I don't want you to think of it as like a formula you have to memorize, because you should be able to figure it out. I mean, it makes sense that the velocity of, if you know the velocity of one object relative to the second, and you know the velocity of the second object relative to the third, then the sum of those two is the velocity of the first object relative to the third, right? That should be a common sense thing. But if you can't get that, you should get this, that this is the general formula here. Okay, come back to this problem. We now understand how to relate the velocities, and we can therefore say that the velocity of the swimmer relative to the ground is the velocity of the swimmer relative to the water. Now we really want to have a coordinate axis just to make sure we get our signs right. So since everything currently is going to the left, I'm going to call to the left our plus x direction, and go ahead and figure out that the velocity of the swimmer relative to the water is plus 1 meter per second in the x direction, and add to that the velocity of the water relative to the ground, which is plus 2 meters per second in the x direction. These are vectors, so let's start writing them as vectors. That's the velocity of the swimmer relative to the ground, which we can add these like scalars because they're both in the same direction. So that gives us 3 meters per second in the x direction. So the velocity of the swimmer relative to the ground is 3 meters per second in the x direction. So therefore, how long do they take? So therefore, delta x equals v delta t, where in this case, v is 3 meters per second. So therefore, delta t is equal to 100 meters over 3 meters per second, which is 33.3 seconds. Okay, let's do another example. So now what if the velocity of the water is flowing in the other direction? What if the velocity is the velocity of the water is flowing, the swimmer is swimming against the current, right? They're swimming against the current, and the velocity of the water is, I guess we made it 2 meters per second, so let's make it 2 meters per second downstream. So then we ask, And so, yeah, 2 meters per second downstream. So then we can ask, how fast is the swimmer swimming relative to the ground? The swimmer swimming relative to the ground plus 1 meters per second in the x direction. That's the velocity of the swimmer relative to the water, plus the velocity of the water relative to the ground. Well, now notice that the water relative to the ground is in the opposite direction from the plus x direction, so it's minus 2 meters per second in the x direction. So the velocity of the swimmer relative to the ground is minus 1 meters per second in the x direction. I didn't need parentheses there. And so then we say, okay, so how long does it take for the swimmer to go 100 meters? Well, delta x equals v delta t, because this is a constant velocity formula. In this case, delta x is plus 100 meters, and v is equal to minus 2 meters per second. And so delta t is equal to minus 50 seconds. Wait a second, minus 50 seconds? Well, duh. Probably you all saw that the water is carrying the swimmer downstream faster than the swimmer can swim upstream, so the swimmer never makes it the positive 100 meters. They never make it the positive 100 meters, right? So if we're asking how long it takes them to go from those 2 points on the shore, they're never going to make it because they're being pulled the other way. Or, so you got to be careful, you got to pay attention to those minus signs. Or you could say, how long does it take the swimmer to move 100 meters in either direction? Well, okay, then, except for the fact that you all said, what are you talking about? Because I put the wrong number in that equation. That's not minus 2, that's minus 1. But anyway, okay, back to that. So it would be minus 100 seconds. Still, doesn't make sense. That's before we got started, minus 100 seconds. Although maybe it does make sense. Maybe minus 100 seconds ago, the swimmer was farther upstream, and they're being carried backwards, right? So the minus signs can make sense. But in this case, we're just going to say, oh, okay, the swimmer, we asked the question, how long does it take the swimmer to go from position 1 to position 2? And this swimmer is never going to make it from position 1 to position 2. It will take them 100 seconds to go 100 meters downstream, but they will not make it 100 meters upstream. So the next thing so that's velocity addition, right? But the next thing we want to do is now think about what happens if the swimmer is swimming across the river instead of down or up the river. And that's where we're really going to get into two-dimensional motion.